Everybody, my name is Jake Domingues, and welcome to my Lab 5 free throw physics. So first of all, this lab is going to analyze forces, velocities, angles, and positions of the NBA free throw. Analysis from a real model in an NBA game from Kevin Durant, and a computational model to test the different variables and change their values and predict different situations. My initial hypothesis was that the success of a free throw will be based mainly off of the release angle of a basketball, but this will change as we'll see. The basis of this lab is, of course, thanks to Newton's second law, the momentum principle, which describes the momentum of an object with respect to time, in that the total force on an object is equal to momentum change divided by time change, or F equals ma, of course. So my models, I had an experimental model, a video I found on YouTube of Kevin Durant shooting a free throw, which was recorded from the side, to create a semi-accurate model of the motion of the ball in 2 dimensions. Then I created a computational model using GlowScript. This was just based off of the initial conditions that I recorded in the video from Kevin Durant and from the tracker model. Speaking of the tracker model, here's the video. As you can see, shoots the ball, recorded from the side, successful free throw. So here's the tracker system that I used. You can see that I calibrated the dimensions using Kevin Durant's height as well as the NBA standard court size. And then you can see that I tracked the ball using a bunch of different keyframes to find the ball's position over time. Here's the video of my computational model, which is the ball being shot in the air, as well as the position over time graph of the y velocity. Oops. Here's all the functional code for that computational model, but basically all it is the initial conditions of the ball. So the ball's mass, the ball's initial position, the ball's initial velocity, which is what I ripped from tracker of when Kevin Durant shot the ball. The instant he shot the ball, that's the velocity, as well as the time, and the delta t coming from the frame rate of the video, and obviously gravity. Then the while loop, which is from t starting, which is 9.83 from the video, and ends at 10.83, which is when the shot goes into the basket. This is pretty simple calculation using the constant force due to gravity, which is the only force that the ball experiences in the air. Then I used iterative calculation using the velocity and position update formulas to calculate the time, and then obviously it advances the clock and prints with a trail. So here are my results. First, the y position, the most important one. As you can see, this is a parabola. If we go back to the video of the computational model, you can see that it also produces a parabola, which is a good sign. That means that our information is likely accurate. Then another way to prove that this might be true is that we only have one force, so we will have a constant acceleration. Therefore, integrating that twice will give us a parabola in the negative direction, since we have a negative acceleration in the y direction. Here's our y velocity. Again, calculating that slope, it's 9.95, which is close to 9.81, which is the acceleration due to gravity. There's many different things that could affect this error, but it's generally close. Here's the x position. We know that the x position is going to be a constantly decreasing line because there is no force on the ball in the x direction. And then here we can see once the ball is shot at around 9.8 seconds that it's pretty much constant along that line. So our system is the ball, and both models, pretty simple. The surroundings is everything that affects the system. So in this case, it's the earth pulling the ball down, since we didn't calculate that equal opposite force. Technically, Kevin Durant also applies a force on the ball to shoot it, but we're only worried about the speed and release angle of the ball, so that's outside of the time scope of these experiments. So lab questions. Steph Curry shoots with a consistent release angle of 58.1 degrees and is 6'2". So how fast should he throw one of his balls up to get the free throw in? So I created a new computational model for this. First, I had to calculate like the amounts of the x and y using just some trig. Tangent of 51.8 is around 5/8. And then I calculated his height to be obviously shorter than Kevin Durant at 6'11". Then putting all those informations to a new graph, I also made a basket out of 2 points. So the blue point, as you can see here, is sort of the backboard, and the red point is the beginning of the hoop. As we can see, that path would lead to the ball going into the basket. And I also created a system where I could change the velocity of the ball very easily. So this magnitude ended up being 7.547, and as we can see from the path, it goes into the hoop. Nice. So what does it mean? There is a increase in the y velocity at the beginning of KD's shot that we tracked in the video. Why is this? Well, the increase of the y velocity at the beginning of the shot is due to the force that he applies from under the ball to push it into the basket, basically. Once he lets go of the ball, the only force of the ball is due to gravity, which creates that constant force, which allows us to do all these nice calculations in the experiment. To calculate this increase, we could set up a sum of forces on the ball, then use an iterative analysis using the computational model to see what the force would need to be to create the final velocity showed in the tracker graph, which, as you can see at that peak, it's like basically 5 meters per second. And yeah, that's it. I hope you enjoyed. Thank you so much.